All right, so now we're going to get into the application of z-scores. So I was trying to give you a little hint there that the purpose of z-scores is that if I could take a value x and convert it into a z-score. So it's a way to figure out probabilities. So a study reported that the length of pregnancy from conception to birth is approximately normally distributed with a mean of 272 days and a standard deviation of 9 days. So I know I gave you this data before and gave you something a little different. Just so you know, when you look up data, it's going to change quite a bit every time you look it up. But anyways, what proportion of pregnancies last less than 259 days? So we are asked, what is the probability that X, right, is going to represent days of pregnancy, that if I randomly grab somebody and I recorded the length of their pregnancy, what is the probability that that length of pregnancy would be less than 259 days? So anytime you talk about less than, this is going to be area to the left. So as you see here, it's that same representation here. We got the mean is 272, the standard the X value is 259, and this is what we're looking for. We're looking for what proportion of my pregnancies would last at 259 or less days. So you can also have an inequality there. So one of the things we can do is we can convert to z-scores, because we know z-scores gives us probabilities. So I need a z-score for 259 days, because that is my X value. That is what I'm interested in. All right. So if you remember what a z-score is, it's going to be X minus the mean divided by the standard deviation. So X is here. This is my random variable that I'm interested in, 259. And I am going to subtract the mean of 272. And I'm going to divide by that standard deviation of 9 days. So as a reminder, you probably want to put this top part in parentheses if you want to do this on your calculator at once, or if we do a bit at a time. 259 minus 272 is going to be negative 13 over 9. So negative 13 divided by 9 is going to be a negative 1.44. So remember, we're going to round 2 decimal places. Technically, it's 0.4 repeating, but we're rounding. So that means if I go back here, this gets converted to, my mean now is 0 because I'm talking about z-scores. And this value now is represented by the z-score of negative 1.44. So I just took everything from X values, I converted it into z-scores. So now what I'm really trying to find here is not the probability that X is less than or equal to 259 days, but the probability that I'd have a z-score that is less than and equal to negative 1.44. So we just converted everything to z-scores so we can use that z-table. Using that z-table, negative 1.44. And remember, because we're looking at a less than, we're looking at area strictly less than, or sorry, we're just looking at area less than the z-score. This area is going to be 0.0749, or is going to tell us that the probability that the mean length of pregnancy is less than or equal to 259 days is 0.0749. So the whole point of these z-tables is we can take values that are our X values, our random variables, we convert them into z-scores, so we standardize them, and then because we standardize them to this z-score, we can use a z-table for the probability. So the whole purpose of designing the standard normal curve and doing z-scores is that we could take any value, basically all normal distributions, basically follow the same shape as shape and principles as far as their standard deviations go. So we just standardize it to making all our curves look like the standard normal curve. And because we can do that, we can find the probabilities of anything as long as it comes from a normal curve. All right, so same problem. Once again, pregnancy is normal, the length of pregnancies is normally distributed with a mean of 272 days and a standard deviation of 9 days. Now we want to know what proportion of pregnancies, oops, let me pick a new color. What proportion of pregnancies last longer than 280 days? So we're looking for longer, so we want the probability that X, which is a length of pregnancy, that if we randomly grab somebody who's pregnant and we record their length of pregnancy, what is the chance that pregnancy is going to last longer, so greater than 280 days? So anytime we talk about a longer than or a greater than, so we got this greater, X is greater than, that means that we're going to look at the right of the score. So we're looking to the right. So when we find Z-score, we're looking to the right of it. But like I said, this distribution is showing us the same thing. The distribution is centered at 272 days. We're interested in the probability of having pregnancies longer than 280 days, so we're interested in this area here. So we're going to go through the same process again, is we need to convert this 280 into a Z-score. So it's always the value that we're looking at here is the one that we're converting into a Z-score. So we need Z-score of 280 days. So we'll have 280 days, subtract that mean of 272 days divided by that standard deviation of 9 days. So that is going to be 8 over 9, or 0.8 repeating, but we're going to round 2 decimal places, so 0.89. So that means I can convert my problem. I'm not looking at X being greater than or equal to 280, but I'm really looking at the probability that the Z-score now is over 0.89. So I'm just taking, like I said, just taking our score and converting it into a Z-score. Now remember, what's going to happen here is that when I use my Z table, I look for my 0.8 and then I look for my 0.09 here. Remember, this is still area to the left. Remember, sorry, I forgot to convert that all to Z's. So we're looking to the area to the left. So if I want the area on the other side, this area right here, which is what I really wanted, so I wanted to the right, I just take 1 minus 0.8133. And that is going to give me 8133, 0.1867. So the probability that, or the proportion of pregnancies that last longer than 280 days, or the probability that somebody's pregnancy lasts longer than 280 days, is equivalent to my Z-score is greater than 189, which is equivalent to a probability of 0.1867. So just as a reminder, because we're rounding Z-scores and everything here, that this is all going to be it's approximations. So these should not be exact values. So approximately 18.767% of pregnancies should last longer than 280 days, or the proportion of pregnancies that last 280 days is approximately 18.67%. All right, and our last question. A pregnancy is considered full term if it lasts between 252 days and 98 days. So we are looking for P. So like I said, proportions of probabilities, these are the same thing. The probability that I would have a pregnancy, which we're going to call X, is going to last between, or sorry, the days of my pregnancy, which we call X, is going to be somewhere between 252 and 289 days. Okay. So we need to go through that same process again. We need to find z-scores. So I need a z-score for 252, and I'm going to need a z-score for my 298. So not really much has changed here because we still have that same mean of 272 days and a standard deviation of 9 days. And we 289, we still have that same mean of 272 days and that standard deviation of 9. So if you plug this all in a calculator, remember to put parentheses around the top if you do it all at once, which I'm going to do this time around. And my z-score here is going to be negative 2.22 if I round to 2 decimal places. And for 289 days, that is going to be 2.89. So we're going to negative z-score and a positive z-score. So this image here showing me what I'm looking for, this area between these two z-scores. Well, if you convert this all to z-scores, this means I'm looking for a z-score between negative 2.22 and 2.89. So I'm really looking at the probability that my z-score is between those two values. Okay. We're going to go to my z-table and figure out these areas. So remember, we're looking for 2 z-scores. Or we got 2 z-scores, we're looking for 2 areas, and everything's going to tell us the area to the left. So the area to the left of negative 2.22, well, that's just going to be, there's my negative 2.2, and then there is my other 2, my 0.02. And we see that this area right here is going to be 0.0132. Now we just need the area that is going to be to the left of 2.89 or less than 2.89. So we go to my other table. All right, just barely fit this on here. So I'm going to need my, where is it? 2.8 right here. And then we're going to need that 0.9, which is right here. So we see that this area here is going to be 0.9981. So this area right here in between them is going to be the larger of the z-scores, or sorry, the larger of the areas minus the smaller of the areas. So the area between negative 2.22 and 2.89 is going to be 9981 minus 0.0132, sorry, is going to be 0.9849. So the proportion of pregnancies that last between 252 and 289 days is going to be 9879 or 98.49%. So the chances are if someone was pregnant that their pregnancy would last between, we'll make it full term, basically between 252 and 289 days is 98.49%. which is really kind of what we would expect to see. We would expect that a large proportion of pregnancies make it to full term. All right. So the last part here, and this is the part we're going to do this again with a TI-84. Let's first do it with our z-scores. So we have that the mean lifespan of a dog is 13.42 years with a standard deviation of 2.36 years. We're going to assume that the lifespan of dogs have a normal distribution. Use the areas. Sorry, I didn't put the images on there. Use the area, the images for a following problem. So we're going to find the areas. So first one is, what is the probability that a dog lives less than 10 years? So we're looking for the probability that X is less than 10 years. So we're going to be looking to the left. So area to the left. What is the probability that dog lives more than 15 years? Probability that X is greater than 15. So when we're talking about greater than, this is when we're looking to the right. And what's the probability that a dog's going to live between 10 and 15 years? And we know that this is where we're going to look at an area in between two scores. So we're going to move this all over to the Z table and work through this. Okay, so we got our mean standard deviation, and then I wrote all our problems and probabilities. So the first thing we need to do is we need to find a z-score for X being 10, so we can figure out how to convert this into a z-score. And then we need the z-score for X being 15. Because as we see, the only thing we have to worry about is 10s and 15s, so we need those two z-scores. So my z-score is going to be 10 minus 13.42 divided by 2.36. And then my second one, the z-score is going to be 15 minus 13.42 divided by 2.36. So those two z-scores are going to be 10 minus, what did I say it was 13.42 divided by 2.36. This one, if we round it to two decimal places, is going to be negative 1.45. So that's nice because that's one we had to find already. And then this one, if we look at 15, then the z-score is going to be 0.67. Okay. So like I said, if I convert this all into z-scores, then this is really the same as looking for the probability that X is less than or equal to negative 1.45. This is equivalent to looking for the probability that Z is, is greater than, because we're still looking at greater than the z-score for 15, so 0.67. And then my 10 and my 15 are converted to a z-score of negative 1.45, Z less than 0.67. So like I said, just taking those scores and convert them into z-scores so I can use my z table. All right, we're going to get rid of this part because next I'm going to need my areas. More importantly, realistically, what is it I'm going to need? So remember, for this first problem, because I'm talking about less than, I am going to be looking to the right. So I don't have to do anything special here. I need to know what the area is to the right of a z-score, or the left of a z-score of negative 1.45. I think I said right by accident earlier. We're all looking to the left. So negative, let's use something more colorful than that. Let me do that again. There we go. Now we can see a little easier. We looked at negative 1.4, and now I need my 5, which is up here. So this area right here, everything to the left of a z-score of negative 1.45 is going to be an area of 0.0735. Like I said, that one we had found earlier, actually. So that's going to answer my first question here. Was the probability that a dog is going to live less than 10 years? The same this question as what is the probability that my z-score is less than negative 1.45? And the question of that is, it's going to be 0.0735, or a little over 7%. Okay, so my next part here, we are looking for the chance for the probability that a dog lives longer than 15 years, or the probability of my z-score is greater than 0.67. So we are looking to the right. So we need this area. We know the z-table is actually going to give me this area though. So let's go find that area to the left. So if we look for that area to the left, we need that 0.6 and then that 0.07, and we see that the overlap is going to be here at negative 7486. So this area less than the z-score of 0.67 is going to be 0.7486. So we need the area that is over here actually. So the area that we actually need is 1 minus 0.7486. So 1 minus 0.7486 will leave us with 0.2514. So that would mean that this area here is going to be 0.2514, or in other words, the probability that a dog lives longer than 15 years, or we have a z-score greater than 0.67, is going to be 0.2514, so a little over a 25% chance. Okay, so the very last bit of this, we have most of our information. So for C, I'm going to write my distribution over here for C. So we need to be in between these two scores. So like I said, I know this area, and I know this area. So I know the area to the left of 0.67. I know the area to the left of negative 1.45. So it's just these areas that are to the left that I need, because this one we're going to subtract from this one. So what that leaves me with here, that this area is going to be the difference of 0.7486 minus 0.0735. 0.786 minus 0.0735 is going to leave me with 0.6751. So the probability that a randomly chosen dog is going to live between 10 and 15 years, or the random z-score is between negative 1.45 and 0.67, is going to be 6.6751, or a little over 67, almost 68%.